But as promised, they will be back by Friday. Didn't quite make today. People are doing well on the part we've graded so far, I would say. But
Is that homework you posted yesterday?
yeah, it's not that hard. Did you guys, actually I tried to send a notice that the homework was posted, but it turns out the Blackboard only has last year's class list, and I spammed them twice. So I'm sorry about that. If you hadn't seen it, I did post it yesterday morning. In general, I'll try to post the homeworks on Friday, or at least on the weekend. Okay, so let's start. Oh, sorry, we have a tutor. You can stand up and introduce yourself.
Hey y'all, I'm Zach Shelton, one of the tutors for P221. Since I imagine a lot of you know, class was originally supposed to have an SI here, and it doesn't. So you have us, there are three of us, myself, Amit Mizra, and Joseph Abish. And a lot of you aren't familiar with the tutoring program on campus. You can go to ESS's website or to tutortrack.case.edu. That's tutortrack.k as a word. Sign in. It's a very straightforward interface. You can sign up for an appointment with any of us for free. That's about it.
Great. Any questions? No? Okay.
All right.
Thanks. All right, so let's go on from where we were. Wow, almost no chalk. I think it hides somewhere. I don't know where. Ah, the mother lode. None of it's white. Oh well. I will lecture in yellow today. Looking back at my notes, I'd forgotten to tell you one thing about complex numbers. So let me just say it real quick. If we have a complex number, C equals A plus IB, for some perverse reason, on Monday I was writing it as R. It's fine, it's just a variable name, but C is more common. What I did say was that because I can just simply algebraically multiply and divide both terms by a number like that, then I argued that this is the same as writing the complex conjugate, the magnitude of the complex number C times e to the I phi, where the tangent of phi is b over a. And we think of this as being a triangle with that being b and that being a. Right? That's how I think of a complex number. And if you want, and I didn't really emphasize this, this is the imaginary axis and this is the real axis. So in other words, there's a length a over the square root of a squared plus b squared in this direction. That's sort of a direction cosine. That's the overall length of it. And similarly, the b-intercept is, the imaginary intercept is there. And that's phi. So you should be able to think this way or that way. You should be able to go back and forth between them. You should know all those things, okay? Now what if I had, and for some reason I had one complex number divided by another. So C1 divided by C2, where that's A1 plus IB1 over A2 plus IB2. You can start manipulating this. One thing you may have seen is you can multiply this top and bottom by A2 minus IB2. Then the denominator will become real and the numerator will be kind of a complex mess. But another simple thing to do is just say, well, okay, I'll put it in these terms with the as an amplitude and a phase. This, by the way, we're going to use this term a lot in quantum mechanics is a phase, right? Because what we're saying, well, sorry, I'll come back to that. So that's the phase. So an amplitude times a phase. And so then this is just C1 over C2 divided by e to the I phi1 minus phi2. Right? That's how you divide two numbers of an exponent. Coming back to the notion that this is a phase, this is the length of C of the complex number. And the angle phi is saying whether you have a real number or an imaginary number. If phi is 0, it's just real. Basically, it's just A. If phi is what? Pi over 2, right? Then it's all imaginary. A final comment, what if I did something like this? What if I said I had a complex number 1 plus I times 2? Fine. What if I said, let's take the square root of that? Or something simple, let's take the square root of I. What's that? Very simply, if I'm going to represent the complex number that way, and then I have to take the square root of it, it's the square root of the complex of the magnitude. And that looks complicated to write, but it's straightforward. This is just a real number. It's a squared plus b squared, square root. I take the square root, that's quarter root of a squared plus b squared. And to take the half power of something in the exponential is just to divide the exponent by 2. So the square root of I, well, let's think a second. I is e to the I times pi over 2, right? Because that's cosine of pi over 2 plus I sine pi over 2. I just said this a second ago, but here I'm writing it out. That's 0 and that's 1. This is I. So that's just e to the I pi over 2 to the 1/2. It's just e to the I pi over 4. So I can think of imaginary and real. Okay? Here's I. That point is I. This point is 1. If this is unit length and that's unit length on this axis. And somewhere here, at an angle of pi over 4, that point is the square root of I on the complex plane. Okay? So now you guys know how to take the root of a complex number. All right. Just a tad of math. I'd forgotten to mention this, and I think it's worth knowing. Okay, so back to more physical things. We finished at the end of last lecture with Schrödinger's equation. I'll write again. It's a kinetic energy term plus a potential energy term equals a total energy term. All right? And for a given problem, we solve for phi. Right? I like the way this is sort of a academic or physicist language for a given problem. So if any physical situation is a problem, any given physical setup, we would know V, the potential, and then we would solve for psi. And then I mentioned that then we'll interpret the outcome as psi star psi. This will be the probability of x occurring and t occurring. And we're going to come back to this. We will go through examples of how you work that out. One thing to note, though, is that psi star psi is what? In terms of a complex number, is that complex? Psi star psi? Is it real or imaginary or both, or you don't know? So remember that, and I kind of mentioned this, but let me just say it again. Any complex number, even if it's a function, some god-awful function, a square and a cosine and an exponential, all that mixed together, ultimately, for any value of x, any value of t, it's just a complex number. C equals a plus ib, which can be written this way. And so C star C is C star times C times E star. I just stick a minus sign wherever there's an imaginary number. C magnitude is real, so star of it doesn't do anything. So that's C squared, and then that's e to the minus I phi times e to the I phi, e to the 0 is 1. Okay, so that's always real. Independent, I mean, I could give you some weird function and I say psi star psi. It might not actually algebraically be obvious that it turns out to be real, but it will be. So that's good. So that makes sense. You might have been a little concerned because the Schrodinger equation, for the first time, I think in your physics career, it's a fundamental equation about fundamental properties of matter, and it's got this I in it, right there, boom, it's a complex equation. And the fact is that psi, not in all cases, but in many cases, will be complex, okay? But that's just, just hang with the math, go with it. Psi has no physical meaning directly. P does, the probability where you take a complex number. There's an interesting homework problem at the end of chapter 4 where you can show that you can reformulate Schrodinger's equation as two real equations. And it's basically analogous to breaking up the wave function into an imaginary, this piece and then that piece, and you solve a real equation for A and you solve a real equation for B, and then the full wave function is just adding them up. So, the fact that it's complex shouldn't bother us. The probability is real. So, let's consider the wave function. Let's consider the problem of a free particle. What do we mean by a free particle? Doesn't cost anything? No. What we mean by a free particle is there are no forces acting on it. To say there are no forces is to say there's no potential. Strictly, it says to say the potential is constant, because then the force, which is a derivative of the potential, is constant. But ignore that. We just call it, we'll take it to be 0 for convenience. And then the Schrodinger's equation is just this. Okay. And then, what did I say? We guess a solution. I'm going to guess that the solution is e to the I kx minus omega t. And of course, we're taking baby steps here. Of course, that's the solution. In fact, if you remember, I constructed the Schrodinger's equation by starting with this and working the other way. But fine, pretend we hadn't done that. Pretend Monday didn't exist. I just gave you Schrodinger's equation. Here it is with no potential. And we guess that. So let's plug in minus h bar squared over 2m. I'm going to take the derivative of this twice with respect to x. Isn't it obvious that ik comes down once, twice? So I'm plugging in here. Plug in psi. So ik comes down twice, and then I could write a times all this junk, but that's just psi. And then on this side it's I h bar, and I take one derivative with respect to time, and I think it should be clear that that's I times omega with a minus sign, comes down out of the exponential, and then all this junk goes along, and that's psi. And so psi cancels. I've got to be careful here. I'm doing this slow, but you've got to be careful. You got i's floating around, you got minus signs floating around. You got to keep your, you know, keep yourself together and not get confused with these. So I have I squared is minus 1 times minus. So this is h bar squared k squared over 2m equals I times I is minus 1 times the minus sign is plus 1 is h bar omega. And now I have to rely on my original quantum definitions, which, as I said, that now in quantum mechanics, that is the energy. Right? That's how I derive Schrödinger's equation. Okay? And of course, I also know that h bar times k is p. So, okay, so I basically showed that I guessed this and it works out. I have this relationship, which totally makes sense because this is also written as p squared over 2m equals E, and that's right. So this all works. So I basically just showed that this is a solution. It had to be because I constructed it. In fact, I constructed the wave function, the Schrödinger's equation, starting with this. Okay, but this is called this is the solution for a free particle. Let me talk a second about it. So let me make just several comments about it. This is called a plane wave. This is a plane wave. Okay? Okay, fine. So it's a wave because one is it moves towards plus x. If we'd had the positive sign, it would have moved towards minus x, right? It's a simple thing. I talked you through in detail, right, on Monday why that's a wave traveling towards positive x. Another comment is that if I want to think about it, well, this is complex, right? And so a way to think about it, at some fixed time, if I plot things versus x, and I have the imaginary axis here, and the real axis there, okay, so let's say t equals 0 for convenience, so that term just drops out at this moment in time. With x is 0, this is 1, so that's my value. Let's say this is 1 here. There's 1 on the imaginary axis. And then as x moves on, when k times x is pi over 2, we've come up to here, okay? And then it goes back behind and spirals, etc. Okay, so the value of it, as I travel along x, the magnitude stays constant, and it just is oscillating between being positive real to positive imaginary to negative real to negative imaginary, and it's like a circularly polarized light in a way. The other thing, another comment is that it's a funny thing. It's a funny thing, especially if I want to think of this as a particle. It's infinite in y and z. If it's really a particle in space, and here's x, and there's y, and there's z, there's no value of, I write it down, and I haven't written y and z, and that's to say whatever value it is at some value of, at some location in x at some time, it's the same out to infinity that way, and the same out to infinity that way. So it's infinite in y and z. And the fourth thing, and this is really kind of a problem, p of x of t let's calculate it. It's equal to A, which could be complex, times A star times A, I mean. This is embarrassing to write down because it's the minus sign, that's this complex conjugate. And that's the straight value of psi, the phase part. And of course, these two cancel, and that's 1. So it's A star A. The probability of this thing plotted versus x, it's a slightly different graph that I drew over there. The probability of x plotted versus x is 1 for everywhere. Okay? And then I just need to keep walking. So this is the solution. If I had a dog and I wanted to find its wave function and it was sitting still, or even it had some energy, so it had some momentum and it was just moving along. In fact, this is when it has some finite momentum. If E is 0, K is 0. So I didn't solve that. I solved it. Dog's moving along. It's everywhere. It's got an infinite extent. And that's a problem. So let's look at this mathematically a little bit. This is the movie. Oh, that turns the lights on. That's bright enough. This is the movie part of the lecture. Good. Okay, so there's a wave. I'm going to drop time for a minute. I don't care about time. Let's just talk about this wave versus x. Oh, and I'm looking for this big stick. There's a big stick. So I can point at the screen. Anyone seen the big stick? No, too bad. No big stick. Usually lives over there. No. Okay, fine. Well, all right. So there it is. Here, I take that wave and this is, I want to explain what I'm doing here. I'm graphing waves, and in a while, probably won't get to it today. On Friday, we're going to talk about Fourier series, which you may or may not have heard of, and is going to be in your life a lot later. And that's rather mathematical. On here, I just want to do it like in a really brute force fashion. I used a mathematical program here, but all I've done is plot a wave. Top graph, I just plotted that wave. In this program, I created an array of points in time, and I mathematically calculated e to the ikx, and that's, I can't remember the real or the imaginary part. Look, it's the real part because it's maximum at x equals 0. So I just took the real part of e to the ikx, and I asked my program what that was. Okay, and that program can calculate complex numbers. So just pure brute force math, but not even like fancy math, just calculated math. Okay, so then in the next graph, I show the same basic blue wave, and I haven't mathematically added, I just superimposed, I can use the cursor. I superimposed in red a very similar wave. I made it half the amplitude. And I made it, you see this, slightly lower, 0.95 the value of k. Remember, k is 2 pi over lambda. So if I make k smaller, I'm making lambda bigger, lambda the wavelength. Okay, so you see I picked a slightly smaller value of k, and then what happens is the wavelength's a little stretched out. Okay? Here I add the two of them. It's a little more like it. This wave here is no longer just infinite in space. Well, it is actually infinite in space, but at least there's something, it's got some features to it. Okay, so let's do it again. So here I've superimposed the same two waves as before, and now a wave again, half the amplitude, it's drawn in, what did I add? I think I added green, with 1.05 times k, so a slightly shorter wavelength. And here now I just simply add them. And if you can see there, right there, the wave has completely almost vanished in this node between this kind of pulse-looking thing. So this is the meat of it. This is the meat of it. If I take a single k value, I got this infinite wave. This is pure mathematics. We'll talk about why it's physics in a minute. Pure mathematics. Take a single k value, I get an infinite wave. I take that k value and I add a little bit higher and a little bit lower k values with half amplitudes. I add the three waves together, just pure crunch numbers. You could do this on your calculator if you had enough patience and graph it on a piece of graph paper, okay? And I get that, and I've created something that looks kind of like packets. All right? So that's the first conclusion. And here, yikes, this, different screens is messing me up. That's just a graph of the 3k values I picked, right? Here's the center one and the two extra ones. This seems really simple, but this is going to get real subtle real quick, so pay attention, okay? Okay, that was that. Now let's do something else, similar. I hope this is formatted for the screen. It is, good. Except that guy's in bad shape. Let me move him on screen. All right, and he's too big. Hold on a sec. Okay, so that's what I just graphed. Okay? 3 different values of k, and I got this thing with kind of a pulse, and then, you know, a gap in between. Okay, that's good. So let's go with it. Instead of taking one value of k and 2 others, I took a set of k's and I've graphed the k values I took, and look what I got. I got this pulse in the center. It looks just like that pulse in the center, just about, but instead of having like a little minimum here and then a new pulse, I don't see anything going out to the edge here. Okay? Here I just expanded the scale. This is that. This went to 20. Now I went to 200. So I see that I have a bunch of packets. Okay, and these are going to represent particles. But if I have this many values of k, okay, instead of having pulse, 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 I get pulse, big blank space, pulse, big blank space, pulse. This is that, just on an expanded scale again. Okay? So what I'm seeing is, I can't remember if that's the end of this. That's, and then finally, if I take this here, this set of k values, and I instead go to this many k values, which is twice exactly as many as that, when I go from here to here, I doubled the number of k values that I picked. Just the, mathematically k here. I've pushed this pulse, if you will, out twice as far. And I've shifted all of these, I've made the spacing twice as big. Okay? So, simple statement is, from this, a real particle, chalk. A real particle, oh, I got white again. Real particle has an infinite sampling of k values around some average k0. Okay? There's just some there's some value of k which I put in units of simply 1 here. And then there's a whole band of k values. And instead of doing a sum on k values, I turn this into an integral. I want to, mathematically. That will take these sort of ghost packets and move them mathematically off to infinity. So that's how I'm going to represent a real particle. A real particle can be made of plane waves, but it cannot be one plane wave. If it's one plane wave, it is everywhere in the universe, period. Okay? If I want to make it like a thing that actually just sits at some finite place in the universe, I've got to give it a range of k values, and I've got to have an infinite, like just a smooth function, an integral, a smooth set of k values with infinitely fine spacing. That's nothing more to say there's just like a function, a curve of k values. Okay? Let's run the third demo. Oh, white chalk all over my yellow chalk all over my keyboard. So, I'm going to draw slightly different conclusions. So now, here's the same sort of thing. Top graph is the packet. I've just zoomed in on the same packet I showed you before, one of those packets. These were the k values that gave that packet. I've kind of changed the scaling a little bit, okay? But it's the same stuff. Let me take a wider set of k values. Remember, initially I took one value of k, and at half the amplitude I had 5% larger and 5% smaller values of k. That's this. Here, I'm kind of going out to, like, 70% lower and 70% higher-ish. I mean, there's a whole set there. What happened to the packet in x? It got narrower. Let me repeat. I'll take a broader set in k, and the pulse in x got narrower. Okay? So this was my first, I'm doing a lot of things here. So let me just remind, I first concluded that a real particle is made up of a sort of a continuous set of values of k. And that created a single packet isolated at the origin rather than a set of packets. Good. That's sort of a little bit mathematical. This is something, though, you're going to live with a lot. I'm seeing a relationship here. This is my second conclusion, my second big conclusion. If I have a broad set of k that's synonymous with a narrow packet, I call it a packet in x. If I have narrow set of k, this is synonymous with a wide packet in x. Okay? Finally, if I quite literally just simply on this axis where 1 used to be my center k value, I just simply take k values uniformly from 0 up to 2. And in fact, I think I just kept going out past 2 up to some memory limit in the computer. And asked it, I used the exact same code. So if I asked you to do this by hand, you'd just been sitting there calculating a lot. All of the wiggly waves canceled everywhere out here, remarkably. And I got this spike at the origin. Okay? So if I take a very, very broad set of k, I got a spike in x. So that's the limit of this statement. Let me erase this and write this down. If I take a infinitely broad set of k, I get a spike. This is sometimes called a delta function. Simply means a spike. Strictly speaking, a delta function is a mathematical function invented by the physicist Dirac in the development of quantum mechanics that the mathematicians hated and for like a long time didn't know how to deal with, but you can use it and it works, and finally a mathematical foundation for it was a delta function is infinitely tall and infinitely narrow, whatever that means, such that the area is 1. Okay, so you do it by the limiting process. You take something that's not infinitely tall, but is pretty tall, and not infinitely thin, and it's pretty thin, and you write it down such that as you take one parameter and make the parameter smaller, it gets really tall and really narrow, and you define it to be equal to 1. And physicists thought that was great, that's a nice function. We use it all the time, and the mathematicians like 30 years later said, okay, it's a well-behaved mathematical function. But they had to come up with a generalized notion of functions to do that. But anyway, it's a spike. It's a delta function right there at the origin. You know what, though? This may seem freaky, but this is just where we started. I started one value of k. I can't write. One value of k is an infinite set of x. When I wrote e to the I kx, that's a wave with one value of k, and it's infinite in x. And it turns out the opposite is true. If I take an infinite set of k, I get one value of x. Okay? There's this absolute symmetry between k and x. Okay? In this sense. Why did it do that? Oh, my laptop went to sleep. Now, power's not on. That's interesting. Okay. Let's run through those just real quick again, right? Just to see how these develop. Many values of k, twice as many k, right? And then finally, boom, boom. Narrower k, broader x, broader k, narrower. Narrow k, broad x, broad k, narrow x. Okay? So this was presented as a purely mathematical exercise. I was just looking at the properties of a plane wave, which seems simple enough, but of course it is a little bit, I am talking about looking at the properties of the function e to the I kx. But nonetheless, actually all this argument works equally well if I just used cosine and sine. I could have constructed the same thing, because in fact, mathematically I was always asking the computer to evaluate the complex number, and then I took the real part, which was always just the cosine of something. Okay? So, but it was just a built-in feature of these plane waves. But of course it's deeper than that. So in quantum mechanics, this is a generic feature. Delta P, this is somehow this is usually called the uncertainty in P, which is momentum. And similarly, this is the uncertainty in position. That the two of those are a constant. If I make this narrower, that gets bigger, vice versa. In fact, which I'll sort of do a hand-waving proof on Friday, but I'll just assert right now, they actually have that relationship. If I multiply my uncertainty in momentum times my uncertainty in x, it can be minimized. The product can be minimized. But the minimum it can get is this particular value, which is h bar, Planck's constant, over 2. Okay? And you've probably heard of this. This is called the Eisenberg Uncertainty Principle. It's one of the hallmarks of quantum mechanics. Okay? And there's lots of ways to talk about it. I've assigned you a homework problem where for the two-slit interference pattern of electrons coming in, the angle theta is related to the wavelength over d, where the angle theta is, that theta off to one of the waves, one of the fringes in the interference pattern. I shouldn't have written that there. Put it right underneath my drawing. Theta is like lambda over d. And you can make an argument, since p equals h over lambda, and the bigger theta is, the more uncertain you are as to where the particle ends up, right? So theta goes like 1 over momentum, which is to say theta times momentum in this case is a constant. So as theta gets bigger, p gets smaller. And this is a crude argument, because I wrote p here, I didn't write delta p. I'll try to be a little more specific later, but this is a version of it that you're going to work out in your homework. If I know where something is, I don't know what its momentum is very well. And if I do know its momentum well, I don't know where it is. And I just showed you the two limiting cases. If I have a plane wave, which is simply e to the ikx, and k is just, h bar k is p, related to the energy, and it is a particle and has one momentum, it literally fills all of space. Okay? And if I ask, where is it? In quantum mechanics, p of x is a probability. I don't know where it is. I know where it might be if I do an experiment. And if p of x is constant, that means it could be anywhere. And it's in that sense I say I don't know where it is. It could be anywhere. If I go find it, it will be in one location. But then at that point in time, I will have chosen one location. It will have an infinite energy, because I showed you that case too. Mathematically, the only way to get it to have one location was to build it up, and I just showed you mathematically, I had to throw in every value of k to get this thing to sit as a spike, a delta function, at one position. Okay? So that's the uncertainty principle. You can't simultaneously determine the position of something and its momentum at the same time. Okay? Let me talk a second more about what I mean by this, though. When I have a particle, and say it's a free particle, initially, it might be in a situation. Remember, mathematically, I first did a thing where I had one value of one wave, and then I added the two little bits of a wave, and I got something that had some sort of beats in it. So I was summing up three different wavelengths. You can have a wave function which is a combination of several other wave functions, and the particle's sort of happy to sort of have those wave functions at once. Now realize, we are talking something that's not classical at all here. If I say I gave a particle a set of k values, which is what we kept seeing, that's a set of momenta. I'm saying it literally has a set of momenta. Ain't that weird? Shouldn't a particle have a volume momentum, Especially, in this case, this isn't always the case, but in this case, the momentum and the energy was just very simply related. P was this, E equals 1/2 mv squared, which I don't think about V anymore, so it's P squared over 2m. That was the energy. So P and E are just directly related. So I'm saying it's a particle that has a set of energies, and I don't know what they are. And as you might intuit, that's not very palatable. A particle ought to have one energy in many cases. The fact is, the particle can be represented by a wave function, which is a sum of different energies and different momenta. And then what will happen is, you will come along and interact with the particle. The sort of way we talk about it is that you will observe the particle, or you will do an experiment. You will measure the particle. And if it was a particle that was somehow, let's just think of the 3 waves that I created, where I had that wave, and then I added up one that was a little bit shorter and a little bit longer wavelength. And these all have slightly different values of P. When I go in and measure it, it will decide, it will pick, in a probabilistic way, one of these. And the language we use is we'll say the wave function collapsed. And it shows one value of the wave function. If I construct an experiment where I ask, what is the particle's energy? And it started out, the particle was well localized because it had some finite spread in P and some finite spread in X. Just like I graphed. In X, it might look like this. And in P, it might look like that, i.e. in K, which is directly related to P. It's P over H bar. So initially, it had some range of X and some range of P, an infinitely finely sampled set of K. When I do an experiment to measure the particle's energy, I collapse the particle's wave function. Whatever that means physically, I have utterly no clue, and I don't think anyone does. Okay? But I collapse the particle's wave function to one value of K, at which point it is an infinite wave in X, and I don't know where it is, but I measured its value in K. Einstein hated this. He absolutely hated this. He hated it for 2 reasons. Well, probably more. I'm not a historian of science, but I know there's 2 things he didn't like about it. One reason is that it's probabilistic. You don't know what momentum the particle will have. You don't know where the particle will be. It's probability. And he famously said, God does not play dice, right? Because even though he overturned classical mechanics, right, he only overturned it in terms of, he only overturned it in the sense that, space and time are now mixed up and there is no absolute time and there is no absolute space and all this wonderful stuff. But he was stuck with the deterministic notion going back to Newton, that you can predict in principle I can write F equals ma, Avogadro's number of times for every little cubic centimeter of material in the universe, and solve all those equations, and I'll know the history of everything from here on out, including every thought you're ever going to have, every action by any person or any atom or any molecule or being or whatever in the entire universe. And this says fundamentally no. No. It's not just that you can't do that as a practical matter. Everything is probabilistic. Secondly, to collapse a wave function, and there's these classic examples where you arrange 2 photons to be in a quantum mechanical superposition of a couple of possible outcomes. And then you measure one of the 2 photons, and it collapses the wave function of the pair of them, and it forces the other one to have been in a certain wave function. And that can be acausal. In other words, I'm saying if I had one of these infinite waves in X, psi was sticking out to infinity, and then I somehow force the particle, that's the wave function, I somehow force the particle to be in one state, okay? Instantly, psi disappears all the places I didn't measure the particle. And that can happen faster than the speed of light. And that, in fact, has been demonstrated. Wave functions collapse that does not obey sort of causal time notions. It's very subtle. There's sort of philosophers in physics who study this and have thought about the theory of this. It doesn't violate causality, but it is extremely weird. And Einstein formulated it in something called the EPR, Einstein, Podolsky, and I forget who R is, conundrum, where this is really illustrated. Feynman once said there are 2 types of people who there are 2 types of opinions about about all of this. People who are really, really bothered by it and people who haven't thought about it very much, right? Even though he was a huge proponent of quantum mechanics. It is really weird. But that's the basic notion. I showed you the math. I explained our weird, we're not quantum mechanical creatures, so this is just weird to us, but this is the reality, and we just have to deal with it mathematically. Okay? So I'll see you guys on Friday.